Okay, take two. So let's take a look at this. This is a wedge anchor, if you will. You drill a hole, you secure whatever you're going to secure around about the sleeve, and there's the washer and the nut. And it secures and wedges against the walls. 1, 2, 3 locations. This is dimensionally that size there. I'll explain that in a bit. Take note. Oh, here's another type of wedge anchor. This screws down, drives a pin further into expand 1, 2, 3, 4. Oh, that's different. This is 4 walls. Very interesting. Now, this has 3 walls. So you see, you got 3 thin walls bending on the steel. If this was soft metal, then even though it says 4 walls, more surface contact area once the wedge comes up. More surface contact area will give you more of a better wedge action. So it theoretically should be stronger. It's much thicker, so it won't grind away. But it depends on the hardness of this, right? You want this to be hard, or you want it to be soft, or you want it to be a combination to be able to meld with the grind itself into the concrete. Interesting, though, as I just showed you, the wedge anchor's there. But look at the threads down here. Clearly, you're not bolting down there. Can anyone tell me, this is a riddle, the way I talk, Columbo style, so playing a little dumb on you. Can anyone tell me, why would they do this? Why would they put threads all the way down there when I don't want to say they're not needed, because I don't want you to be led wrong. Why would they put threads way down here when you can't use them? How about that? Well, you can't use them. The threads are all the same, just so you know. So is this machining? Is this done through machining, that they just make it easy? And you screw it all the way down. You can screw it all the way down and make maybe a shorter version wedge, and you chop this up. Anybody ever think about that? You chop this up and make different sizes? Well, you could, theoretically, simply cutting it up. So in a bind, you could definitely cut a large one and make a small one. But that's not the intent. Just giving you guys a clue, though, a hint, a tip. Now, shout out to the Bolt Depot. They sent me this. Yeah, this one's been sitting around for a while. I've been meaning to get around to this video. And there's another one they've sent me with knurling here. And we're going to do pull-out tests. As you guys know, I do this type of anchor testing. And look at this one. And this one's got threads all the way on it. Yet, it's only going there that far. And this is sort of like a stud on a car. Can anybody explain to me why a stud on a car would have all these threads all the way down? When you're clearly clamping out here with like the tire. But yet they have the threads continue down here. Don't research it. Just tell me. I don't think anyone has the answer for you that you'll be able to find anyway. But can anyone tell me, I'm going to think I'm going to title the video too. Can anyone tell me why they put the threads way down here when you're only using up here with the washer and nut? Or this one actually is all threaded, but with this here. Now, oh, I know. Maybe because you're only going to clamp something up here and you don't want it to run into the threads, something you're going to clamp here. And so, okay, I got you. So then we'd run the nut down here. And now all this is sticking out at that point. So it seems like I can buy a shorter nut if that's the case. So in other words, that's not the answer, guys. That's not the answer. Can you tell me why? Now, let's observe this. I'll give you some more details on this nut. On this screw or bolt, you want to call it. This one has like a built-in washer. This is so it can torque right here at the bottom. So when you're torquing it, it will slide much more easier. And look at the K value. The torque value will be it will be better. It won't be grinding into the material there if it was flat against. Right there, flat. So you say, when do you use a washer? Well, the washer is going to dig right in. If you just did this, this will dig right into the material. As you can see, there's none of that fancy built-in washer, if you will. But a washer, on the other hand, now gives you the, look at that, slippies. Now, how do you know how much force it takes? Well, initially, when you go to torque, you'll get the initial starting torque. You'll get the initial starting torque. So if you were using a beam bar as opposed to click, 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 I don't like click, click, clicks. I like the beam bars. Now, if you're going to do the click, 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 and you want to know the initial torque you need before it starts turning, you can start down low and work your way up until you see the ratchet, the socket driver you have, the socket you have on top of this rotating. at that point, you can say, I'm there. Well, you're beyond, you're right. You know, you want the lowest value you can where it starts to turn. And that's your initial torque. So everything below that is just, it's nothing. So if it takes 80 pounds to get initial torque going, first 80, you get nothing. You got nothing until you start engaging. So the initial torque here, without the washer, is going to be different than when I put the washer on. If you want to know what the washer brings to the table, well, you'd have to bottom this out. You know, where it wouldn't slide anymore. You could probably clamp that closed where it won't come apart. Right here, put a strap on it, and then I would start turning it, and that would give me my friction here. My original. When I start seeing my torque go up, then I know the initial torque, the initial starting torque is, and then I would take this off to see what I gain. Now it's only going onto there. Now I would use my whatever I plan on clamping as the true test. So it'd be a piece of metal, so be it. Now this then I put on, and now I know the initial difference between using a washer and a washer versus that direct metal. So now the initial torque might be higher because it's going to give me a lot more before it kicks in. It's going to be different, right? See how it can glide a lot more. And I can actually sort of test it by doing that already. But it's rotating around that washer pretty easy. It slid down the bottom, slid over it with my hand. You see it right there over the end? I can keep going. Now it's already cycled once down there, you know, with that action instead of me just pushing it. But now let's just try it. Take a look at it. It's kind of down there. It's closed. Let's see if it's closed up. It's about back to original. Now let's try it with just the nut and drive it down. Okay, so I brought it to the initial snugness, if you will, and now I'm trying to turn it at the top of my hand, and it's not spinning much. And it's giving me a lot more resistance. Okay, it just broke. Yeah, it's a lot more resistance. There's no spinning going on there. So you can see that where the washer comes into play, you can do this yourself. Okay, now it broke free. Now it's past that initial bump in the little crown down there. But that was just feeling it by hand. I could feel the difference composed to that as opposed to the other. And that's your starting torque that you're sort of evaluating. But the trick question here is, why all these threads? Why all these threads? And if you pause the video, I'll tell you right now. So if you want to try to guess it, guess it. But if you don't want to learn the answer right now, I'm going to tell you. So pause the video. And the answer is, okay, the major diameter of this whole piece is presented as the same as here. They're not always like that. Custom, they might be larger down here, and it's different. But you can see how this is. Now, if I go to pull on this part here, say it was all solid, necking. Think of necking, how it gets thinner. Well, this would take a lot more resistance, a lot more force to neck it. But if I dissect it a bit and put these spirals around it, removing material, in this case it's thread, it serves two purposes. One for the thread, the nut, and the other to dissect it, remove some material to allow for stretching of the bolt. Stretching of the bolt takes place in here. And so when we go to clamp it, the threads are down there. The threads allow for the stretching. I want you to think of your car studs, for you guys that are mechanics out there. You know the studs are threaded like this, aren't they? And yet we're only using the threads way out here on a car. Well, that's the part behind here that stretches. If we had it all like that, and at the last bit we put 1 inch of thread on it, and say on the other side, on the tire side, on the rim side, it still had this much thread left, well, that's great. It shows you can still tighten the tire. But that's all that's going to be, all that torque is going to take place just within three threads. So you'll have to torque it much greater to get the clamp force, to put tension on there. And that's ultimately can cause your thread popping. And we don't want threads to pop. We want clamp force without threads popping. So you do that by creating stretching and like a spring effect. It's pulling back, trying to pull together. And this creates that pull together effect. For you people that use torqued yield bolts, you would just simply, once you put it back together, you would check it for necking. all these would be the same in here, and you would check the diameter all the way down. And you could say that's pretty good. It's probably back. If it was torque to yield, and you put it in the yield zone, plastic zone, somewhere there'll be a deformation here that's permanent. That it won't be equal all the way through. And wherever you see where it's not equal, then that's where it yielded fully, and it will be in here somewhere. It will yield here. Now, if your threads are really, if it's engaged here, like the rim's hitting on it, and you try to tighten a bolt. All right, so some people try to torque their tires with them down on the ground. It's the worst thing you can do. Your tire's on the ground, it's stuck, and now you're trying to create a clamp force onto the rim, but you have to overcome the friction of the tire being pulled, dragged across the surface to close up the back of the rim and the caliper, brake, the brake pads, not brake pads. Gosh darn it. Rotors, the back of the rotor. So you're trying to drag it across the ground to get them tight. Put it up in the air, chock your tire where it can't spin, and now you'll be able to do the clamp. You'll get the torque proper. But on the ground, anybody who torques their tires on the ground, you're not torquing it. I don't know what you think you're doing. Unless the other tire's off the ground, you can pull a car over into what you're doing. But if that tire is touching the ground, you realize you're going to get torque much easier because the tire and the rim's going to resist your. If it's like that, let's say the rims, instead of being square with the disc. Yeah, I know I said it right a second ago, right? So it's being square with the disc. Say the tire's out like this, and you go to clamp the lower screw. You see what you got to do there? It's got to drag it in, but it's dragging against the ground. So if this tire would drag in as opposed to the left part of the car being drug over, and the tire stationary there. No, you would have to drag it in, but it wouldn't drag it in. You'd get an ultimate torque reading much quicker, even though you haven't created the clamp force. You see what? Now I can do a model of that and do it in real life and show you that it can be loose, even though you got torque. Imagine that. You just put the tire on loose, so don't try to do it correctly. Do it, I'm exaggerating. Put the tire on loose. Don't tighten the lug down all the way. Put it on the ground. The tire's out like that. Now go to torque it. You can torque it at 25 pounds, whatever it calls for. You know you're going to get 25 pounds of torque, and the tire's still going to just move in just a little bit. And when you lift it off the ground, you're going to have this sloppy tire. And so that's why doing a tire off the ground doesn't work. On the ground doesn't work. Off the ground, shock it, and that's how you get your true torque. The way you guys do it, the true torque. And I can show you with the beam bar, the most awesome way to do it. As far as cleaning the threads, the beam bar is the one that I'll show you in future videos how to use a beam bar as opposed to a click-click torque wrench. The click-click torque wrench can get you into the plastic zone by mistake. And plastic zone means it's deformed. It might brittlely break depending on your bolt. And, depending on your bolt. Your screw, however you're attaching to. So however you're attaching, some of the stuff is screwed that way, right? They're like studded now, some of these cars. Okay, so hope you enjoy this lesson. So you're trying to figure out clamp force, and I'll do clamp force video. I've got a clamp force tester, and I have the puller, but also there's a clamp force tester. It's about a $5,000 tool that will do that, and we'll run through some of these. I'll put it in there and show you how the clamp force works and what you get from it. And we'll see if it's I'll show you if it made the plastic range. Probably not with this grade 8. This takes. I don't want to destroy the bolts in my other tools. They're both calibrated, but the other one, my torque wrench is calibrated, and I don't want to, take it out of calibration. I still need it right now. The other tool is calibrated too, but it's designed to be used many more cycles. Torque wrenches, they can give you a range, and it's not worth it to me at this point. But I'll use the beam bar one, and I don't even care if it's out of torque, out of the beam bars. Let me put it this way: the beam bar, in the way I'm going to show you, it doesn't care. It's just self-calibrating. The needle is all you care about. I could actually care less what it's reading. I'll show you how it works, and then I'll show you how to look at it like a finite element program using a beam bar. We'll see it go into elastic mode, maximum elastic mode, and back out, in and out, cycling. And then I'll show you how we'll get it going from elastic into plastic, and you'll be able to figure it out yourself. You'll see it once I teach you it. And then you'll see us go into plastic still, and then it'll take a bump up, and then all of a sudden it will come across it and break off. And you'll see, and that's just like a graph I just showed you. But I'll show you that, and you'll be able to do that with all these bolts, nuts and bolts. You got to remember that the torque specifications are done on new vehicles. They're new. They're not on the bolts you and I have on our car. They're 10, 15, 20 years old. Those torque specifications suck. Those are new bolts. New bolts that haven't been, new threads and everything else. Your threads, we can attempt to wire brush these and everything else. It's going to be nice and clean to go in, but it's not going to be the same torque value. Any material that's left behind when you go to thread this nut on gets stockpiled in there like a gulling. It comes, gives you a torque, the debris in there can back up. We can clean these pretty good, but ultimately the nut is hard to clean and to visually inspect is sometimes a pain. But I don't care. As long as it threads on easily, beyond where I need it to go. So if you put a rim on here, test thread it all the way down to there. And bring it back out. Look if you got any debris on it. If you do, clean this off. Run the nut in again. Take a look at it. Clean it off again until you get a clean nut. If you want a clean screw, if you will, which you're securing to this part. And now you know. Okay, good. I'm clean start. Now who's going to do that? Probably none of you. But if you want to do it right, if you want to do it with the way I'm going to show you, you'll have a very predictable nut and screw at that point. Now put your tire on, and this is where we'll come back to the starting torque. We'll get there. We'll get starting torque. A lot of it's eaten up in the friction, also known as the K value back there on the back of these guys. They're different from that now. Different. Let me jump a little bit. So if you use this as a screw and you're screwing in your tires, because some of them like that. There's a rotational torque that can happen here that will make it so you have to do higher torque. For example, we saw an engine that had it like that. And it said 24 pounds of torque on this, but on the same engine it had the same block. It had studs sticking out, and this time they wanted 23 pounds of torque because you would just be adding a nut to it. On that side, it's a nut, and on the other part, it's a screw, which is 24 pounds versus 23 pounds. 1 pound difference. The screws, I will say the stud at the other end had a double-ended, some barrel in here like this solid, some shank was solid, and then it had thread again. So that was very interesting, their setup. It made me wonder where the stretching would take place. What side would it pull on? It would pull on this and pull on the other side. How equal would the distribution be? I wouldn't know that until I brought it to failure. You put it in my clamp device, we bring it to failure, and then we look at it and go, oh, it broke right here on the front side of the screws of the bolted side, nut side. That's how you learn where the failure is going to be. And also you learn the maximum of that sample, how it behaves. And now you go, okay, there it broke at 100 pounds. So let's to get the maximum clamp value, let's do it at 85 pounds, and we don't go to 100. And we're not, and let's say we're still in an elastic zone at that point at 85%. Again, the beam bar technique, you're going to learn what percentage. And remember, it depends on what you're clamping too. I'm going to be doing these tests, and it's only testing the screw. It's a load sensors inside this device. It's a $5,000 clamp pressure machine. It goes up to 110,000. I have it rated 110,000 pounds. Costs like $700 to calibrate, just so you guys know. It's an expensive tool, but I'll do it for you guys. You don't want to beat them up too much. I'll do it for you guys. And its expiration dies every year. Like this one's dying in January 2024. So I still have some calibration time, if you will. And yeah, I take my bolts and my nuts and bolts very seriously. I value my nuts. I value my bolts. So there's your thread. Did you guys know that about that? Why the thread's all the way down? Not because they're lazy and it was easy just to thread it all. If you guys might have did that, thread it all. Get it? All thread all. and it's actually called threaded rod, guys. So it's, you know, both of us, everyone's, you know, you can call it what you want. You know what, as long as you, because we have to learn that the new dialect is, if you say, hand me that bangy thing, that's the hammer, whatever. And we're going to do some pull-out tests that are trying to make it equal. This just gives me depth in the concrete, makes a larger cone for it to fail. So if I only have this much cover over this, it's a shorter cone to fail, but this gives me a larger cone, not just depth, but a larger cone also allows me to add, clamp like a 2x4. I could clamp a 2x4 with this one and still have plenty of depth left over and for wind uplift, etc. So I'll do this for you, and it would only be for that concrete I'm testing it in. Each concrete's going to behave differently. And so I hope this was helpful for you. And now you understand now. So this would be like a larger washer on a washer. It's, if I was worried about what I'm clamping here, it would dig in. I don't know if you could, clamping a thin piece of lumber, for example, better to distribute the pressure with this thicker washer as opposed to trying to hold that wood in with this small nut. In that case, it would be like a distribution plate. But if it was just steel, and depending on the slotted hole, if it was pretty much a perfect hole, I wouldn't need that washer. But the holes aren't perfect, so this gives me distribution around the hole now. It's about, on this one, this is about not quite an eighth of clearance. See, I just lean it over and I look at it, see the tolerances. So just lean over on one side. You measure that one side, and that's it. That's your gap, and that's your tolerances. You can do it much tighter than that when you step up in bolts, but this one's not going to do that. This should be punching through, so you want to make sure that this distribution, the plate doesn't deflect. This is flat. And there you go. Take care, guys. Did you see that coming on this? The question is, did you see that coming?